Okay, so we are almost ready to start solving the energy eigenproblem of this Hamiltonian. Before we do that, I just want one more result. So I want to re-express our Hamiltonian. And in fact, let me not do it like that. Let me just do the following. This is the simplest. Let me take omega times by a dagger a. And let's see what this is equal to. I just want to multiply it out. Now, a comes with the 1 over square root 2. A dagger comes with the 1 over square root 2. So a dagger a will come with the 1 over 2. So I've got the 1 over 2 there. For a dagger, I've got q minus ip. And for a, I've got q plus ip. So let me multiply this out. This is omega over 2. Q times q is q squared. Q times plus ip is iqp. Minus ip times q is minus ipq. And the minus I times the I is a plus. And we've got p squared. Well, this is equal to omega over 2. I've got the p squared. I've got the q squared. And then I've got plus I. And if I take this I out, you see I've got qp minus pq. So that's just the commutator of q with p. We know that the commutator of p with q is minus I. So the commutator of q with p will be I. And I times I is minus 1. So we just get omega over 2 into p squared plus q squared minus 1. And that's exactly the Hamiltonian. So this is the formula I wanted. The Hamiltonian is equal to omega a dagger a. That's a nice, simple computation. So we'll store that result. Okay. Let me just clean this now. We no longer need it. Okay, good. Now what I would like to do is I want to calculate the commutator of H with A. So let's turn to that calculation next. Good. So I want to calculate the commutator of H with A. And I'm going to use the formula for H that we've just derived. Omega is a number, so I can happily pull it out of the commutator. And then I have to calculate the commutator of A dagger A with A. And when you see this, you should immediately know, aha, let's use the product rule. So first, we take the commutator of A dagger with A, we leave A alone, plus leave A dagger alone, and then calculate the commutator of A with A. Now, the commutator of A with A, that obviously vanishes. Commutator of anything with itself vanishes. And the commutator of A with A dagger is 1, which means the commutator of A dagger with A will be minus 1. Good. So this is just going to be equal to omega minus A plus naught, which is equal to minus omega A. So we've got that commutator. I want you to calculate another commutator. I want you to calculate the commutator of H with A dagger. So this is going to be good practice for you, and you'll get omega A dagger. And there's two ways that you can do it. So in the first way, you can use the product rule as above. So try that. It's just some simple algebra, but it's a nice thing to go through. And then the second thing that you can do is you can dagger the equation we have. And just a few formulas that may be useful for you. If you've got A comma B and you dagger that, well, that's AB minus BA, and you dagger. Now, what does dagger do? It reverses the order of the operators and it daggers each operator. So this would be the commutator of B dagger with A dagger. Okay, so if you take the dagger of the commutator of H with A, you're going to get the commutator of A dagger with H dagger. And then don't forget, well, this is something that you can very easily check, is that H is equal to H dagger. And then under the dagger, a real number is unchanged. So you should know enough to get the commutator of H with A dagger from the commutator of H with A. Okay. Now let's start to solve the eigen problem. So what is the idea to solve the H eigen problem? Well, it's the following. Let's imagine that somehow you were smart enough to figure out one energy eigenstate. So that means the Hamiltonian acting on some ket E is equal to the energy times by ket E. Somehow you figured out one solution. Well, now I want you to look at the Hamiltonian acting on A dagger times E. And I'm going to write this as follows. I'm going to write H A dagger. Then I'm going to say minus A dagger H. I like these two terms because this is a commutator, and we know what the commutator of H with A dagger is. It's just omega A dagger. But I can't just subtract a term, so I have to add it back in again. And actually, I like this term because the term that I've just added in has the Hamiltonian acting on the eigenket, and I know what that is. So now I get there's a commutator of H with A dagger from the first two terms acting on the energy eigenket plus A dagger with the Hamiltonian acting on the energy eigenket. Now the commutator of H with A dagger is omega A dagger. So this is nice. It's just omega A dagger on the energy eigenket plus then the Hamiltonian acting on the energy eigenket is just E. I can pull that out as just a number. So this is just E onto A dagger times E. So actually I can pull off omega plus E onto A dagger E. So if ket E is an energy eigenket, so is A dagger on ket E. And what does A dagger do? A dagger adds one packet of energy. So that's the packet is of size omega to the state. So every time you act with A dagger, you increase the energy of the state by omega. Okay, let's try to interpret this result a little bit. So look at the Hamiltonian here. There's a p squared term that's associated with the kinetic energy. So we have some particle. It has kinetic energy related to p squared. That's the first term in the Hamiltonian. The second term, the q squared, you should remember that the energy stored in a spring that has been stretched by an amount q is q squared. So what this Hamiltonian describes, it describes a particle that is attached to the end of a spring. It has both kinetic energy, that's the p squared term, and it has some energy stored in the spring, which is the q squared term. Don't worry about the minus one, that's just setting where the zero of energy is. Classically, that's got no meaning at all. So when we want to think about our system, what does our system look like? Well, it's a spring, and there's a mass sitting at the bottom of the spring, okay? And what is happening is our spring is oscillating, okay? So let me just copy this. And let's see how to copy it. Duplicate, good. So we'll put this here. And in fact, I'll want one more. Duplicate, good. Okay, so here's our spring. Now what happens is when we look at our spring, it is going to oscillate. So we might start off and the mass is oscillating, as I've shown by this blue arrow over here. It's moving up and down. When we act with a dagger, we increase the energy of the system so that the size of the oscillations get larger. Now the mass is oscillating with a far greater amplitude. And if we act with a dagger again, in fact, the amplitude of oscillation increases even further. So here, the mass is sort of oscillating as you see the pen moving. Here, the mass is oscillating with a much larger amplitude of oscillation, and finally, with an even greater amplitude of oscillation. So that's what a dagger is doing. It keeps increasing the amplitude of the oscillations. So when you act with a dagger, you increase the oscillations of this mass sitting at the bottom of the spring. So what's happened here at the quantum level is that not just any oscillation is allowed. There's a discrete set of oscillations with a discrete set of amplitudes. You can oscillate with this small oscillation. You can go to a slightly larger oscillation, and there's nothing in between. There's no oscillation in between. You can either oscillate with this small oscillation or go to this bigger oscillation. There is no oscillation in between those two. And then you could go to this even bigger oscillation. And again, there's no oscillation between those two. So there's a set of discrete possible oscillations. And how do you move between these different discrete possible oscillations? Well, that's what a dagger does. Every time you act with a dagger, you oscillate with a slightly bigger oscillation.